Right, so we're happy to start this week's scientific program. There's been a slight change, and Ilya Esterlis will give the first talk. Ilya did his PhD in Stanford a while ago. Then he went to places I don't exactly remember, but now he's in Wisconsin and he's going to tell us about chiral pairing electron crystals.
Thanks to all the organizers for inviting me to this very nice meeting. This is my first time here. And so I'm excited both scientifically and also to explore the area. And thanks to Han for agreeing to switch slots with me. Very good. So today I want to tell you guys about chiral pairing and two-dimensional electron crystals. Just for context, everything I'll tell you about will be in equilibrium, but things will be correlated and they'll be quantum. So I hope that's enough. Good. So, and I'll of course explain what all of these things mean as we go along. So to start, oops, this was working a minute ago. Let's try again. Sorry. No, okay, it's okay. I'll just click here. Good. So what is an electron crystal? Well, as the name suggests, it's an electron crystal or solid formed entirely of electrons, and such a state of matter is expected to arise in otherwise metallic systems when Coulomb interactions between electrons far exceed their kinetic energy, and so to minimize the electrostatic repulsion, the electrons will crystallize. Try again.
Power button. No switching working.
No, did I? Is there an off? Oh, maybe I just have to push harder, or just delay it a little bit. Okay, very good. So, right, the idea that such a thing could occur in metallic systems goes back to Eugene Wigner in the 1930s, which is why we also call these electron crystals Wigner crystals. At the time, Wigner was not interested in anything exotic or even in these crystals per se. This was the 1930s. This was around the time that the theory of metals as we know it today had just been laid out by the likes of Sommerfeld and Bloch and Pauli and all these big names. And despite all the early successes of this new theory of metals, Wigner was worried that ultimately these were all essentially free electron theories or nearly free electron theories with interactions being accounted for in some mean field way. And his concern was that some interesting or important physics might be missed by not taking interactions into account more seriously. And so what Wigner did is what every good physicist is trained to do. He took an extreme limit in which the electron-electron interactions far exceeded the electronic kinetic energy. And then he made the observation that in that limit, the electrons should crystallize in order to minimize their electrostatic repulsion. And based on this kind of picture, he was able to make some inferences about the energy spectra of metals and a few other interesting things. And at the end of his, actually second paper on the topic, he made the following observation. So Wigner observed that certain irregularities indicated, and here he's referring to features of his model of crystallized electrons, come in only at those values of Rs for which there's no practical example, where Rs is a dimensionless parameter that measures the strength of the interaction to kinetic energies. Okay, so Wigner understood that for the sorts of metals that existed at the time, the interactions would never really be strong enough for them to crystallize. And he was correct in the 1930s. But we can now fast forward about 90 years, and with modern two-dimensional materials, we now have a class of systems that can in fact be tuned into this regime of exceedingly strong interactions where one might expect the electrons to crystallize, and in fact they do. And now we even have beautiful STM, scanning tunneling microscopy images of the formation of such 2D electronic Wigner crystals. Here I'm showing you a sampling of STM images of Wigner crystals across a handful of different systems. So this, for example, is in a graphene system in a large perpendicular magnetic field in the quantum Hall regime. This is from Ali Yazdani's lab, and you can see the formation of a beautiful triangular lattice electron solid. You should notice the length scale here. It's about tens of nanometers in each of these panels. And so the structure that you're seeing is occurring on a length scale that is a couple orders magnitude larger than the microscopic lattice scale of the graphene, say, in this system. So this is really an emergent phenomenon having to do just with the electron-electron interactions. Okay, this is similar. This is not graphene. This is a transition metal dichalcogenide, molybdenum diselenide. One difference between this one and this one is that these TMDs are known to be more disordered than graphene. And so this electron crystal is actually being warped by impurities, which are these holes with the red circles. So you can see that the electron crystal is sort of warping and deforming in a way to accommodate these charged impurities. But nevertheless, you can see clearly this tendency to the formation of a triangular lattice electron solid. This is yet another type of system. This is a TMD hetero-bilayer with a twist. So there's a moire potential here. And in this case, a electron crystal is observed to form at a certain commensurate filling of the underlying moire lattice. But presumably all that moire is doing is just stabilizing what is already a very strong intrinsic tendency towards crystallization.
Question.
Yes, please.
How small does the electron-phonon interaction have to be for me to call it a Wigner crystal?
As opposed to what?
Charge density wave.
I think so. In these systems, the electron densities are very dilute, and so the electron-phonon coupling is just small. But
it's huge in MOSE2. You have nice polaronic effects. They're very soft.
I see. Well, I mean, for me, I'm happy to call it a charge density wave or a Wigner crystal. I mean, the question is, what is the underlying mechanism? Of course, right? And I think in these systems, given the ubiquitous, so maybe I'll come back to that in just a second. Actually, I'll comment on that. So these are STM images. There's, I think, similarly compelling evidence for the formation of these kinds of electron crystals from other types of probes in a variety of different 2D materials. Multi-layer 2D systems, multi-valley two-dimensional electron gases, even quote-unquote topological systems. Where by this I mean systems where the formation of an electron crystal appears to coexist with some kind of quantized Hall effect. And it's possible that in some of these systems, maybe electron-phonon coupling is more or less important, but I think the ubiquity of the formation of these electron crystals across all these different materials suggests that it's really an intrinsic property of these dilute, strongly correlated electron gases.
The issue is the diluteness, right? That's
right.
Your lattice scale to be of the electrons.
That's right.
Totally different than that of the lattice.
Exactly. So here it's tens of nanometers, whereas the microscopic, graphene lattice spacing is. Well, yeah. So in the TMDs, it could be a bit more important than say in graphene, but I think it's a question maybe to account more quantitatively electron-phonon coupling effects. But my guess is that it's really electron-electron correlation driven, right? So that's a point. So I think at least from what I've seen, it seems in fact that these electron crystals are not something exotic in the 2D materials. They're probably the most ubiquitous ordered phase that we see. Again, that's common to graphene systems, TMD systems, and so on. And so today I want to tell you a few new ideas we have around these electron crystals. So to keep our discussion as simple as possible, I want to consider Wigner or electron crystallization in the simplest situation, which is that of a homogeneous two-dimensional electron gas. So the Hamiltonian we're going to consider for at least the first part of the talk is this one here. It's just p squared over 2m electrons interacting by Coulomb forces. That's it. Okay. So this kind of Hamiltonian describes the state of a lightly doped semiconductor, in which case this m star is just the band mass and some effective mass approximation. And epsilon here is just the dielectric constant of whatever is encapsulating the 2D material. And the ground state properties of this Hamiltonian are tuned by a single dimensionless parameter, the so-called RS parameter that we already met, which measures the strength of the Coulomb interaction energy to the Fermi energy. In terms of the parameters in the Hamiltonian, RS can be written in this way. The thing I want you to observe is how RS scales, first of all, with the electron concentration. It goes as the density to the -1/2 power in 2 dimensions, which means that the strongly interacting limit, the large RS limit, where Coulomb interactions dominate the Fermi energy, is the dilute limit, the low density limit. Okay. And another thing to observe is how this depends on h bar. You see that RS goes as h bar to the -2 power, which means that the large RS limit is also, in a sense, the semi-classical or small h bar limit. So that's a perspective that'll be useful later on. So with this scaling in mind, we can immediately infer the limiting behaviors of the system. So when RS goes to 0, that's the high density limit, interactions are weak, and we expect the system to behave as some kind of degenerate Fermi gas, and it should have essentially metallic character. On the other hand, when RS tends to infinity, that's the strongly interacting limit or the low density limit, then what we're dealing with is a nearly classical solid, and we expect some more insulating-like character. So we can summarize this in a 0 temperature phase diagram, plotted as a function of the electron density. Okay, so as we just said, at high densities, we expect essentially some kind of electron gas where most of the action, well, where the natural picture is one in momentum space, and most of the action is here near the Fermi level, and presumably some combination of RPA screening and Fermi liquid theory gives you a good accounting of the physics here. On the other hand, at very low densities, when RS is large, the system crystallizes to minimize the electrostatic Coulomb repulsion, and it's known that in 2 dimensions, the structure that minimizes the Coulomb energy is this triangular lattice, this close packed structure. And one thing that we know quantitatively about these 2 phases is that the transition between them, that is between a homogeneous electron state and a crystal, occurs when the dimensionless RS parameter is roughly 35. Okay, so that's an estimate that has evolved over several decades from quantum Monte Carlo simulations, but there's now essentially a consensus on this value. And what's important about this number is not its precise value, not that it's 35 or 40 or 32, but rather that it's large in comparison to unity. Okay, because what that means is that there's a very broad range of densities between RS of order 1, when the Coulomb interaction energy is of order the Fermi energy, and this freezing point, let's call it, where what we're dealing with is a very strongly correlated electron liquid. Okay, so there are different ways of quantifying what exactly one means by a correlated liquid. One way that I like is this pair correlation function, okay, G of R. This tells you essentially the probability of finding 2 electrons at distance R apart in the system. And so in the gas-like regime, that's the red curve, when RS is small, you see this G of R is essentially featureless. Okay, and that's because the electrons in the gas regime don't really care about one another's positions. On the other hand, when RS is big in the crystal phase, that's the blue curve, you see these sharp peaks. And the positions of these peaks are just the nearest neighbor distances from a given electron to its neighboring electrons. So this is the signature of crystallization in the system. And what's interesting is that in this correlated liquid regime, that's the black curve, this is at RS equals 20, just a representative value in this range, you see that the pair correlation function retains much of the structure of the proximate crystalline phase. Okay, so this is one way of quantifying what one means by a strongly correlated liquid. And even though we kind of understand the asymptotic regimes quite well, it's precisely in this correlated liquid regime that there are still open questions. Okay, so one outstanding question, and one that's still being addressed today, is are there intermediate phases between a homogeneous electron liquid and a Wigner crystal? Okay, another question, and this concerns the crystalline phase itself, is what is the nature of the quantum dynamics, let's call it, in that range of densities where you're close to the melting point, okay, where the 0 point motion of these electrons is big, tunneling effects are significant, so it's still open what, say, the magnetism is of the crystal and so on. And so the thing I want to tell you about today is a idea for a intermediate paired crystal phase. I'll explain what I mean by that in just a little bit. And also the role of Berry curvature of the host electronic band on this paired crystalline phase. And so we'll see that there is actually a tendency towards pairing of electrons in this intermediate RS regime. And that's going to be driven actually by the quantum fluctuations of the system. Good.
Yeah.
Yes, please.
So those examples you were showing,
Yeah.
of 2D Wigner crystals,
Yes.
what typical values of RS do they have?
Yeah, so they're tunable and they can be tuned actually. So and they're the way they're tuned is just by tuning the density with electrostatic gating. They can be, depending on the material, they can be tuned anywhere from RS of roughly 40, so within this crystalline phase, to RSs of roughly 5. The densities can't be made too high, so you can really sweep through a lot of this range. Yeah, and so actually just to that point, the phase diagram I'm showing you here and the Hamiltonian I showed you is the simplest homogeneous electron gas. It does not describe in any quantitative way, say, a graphene system, even in the dilute limit. But I think a lot of this physics is still common to many of the systems, including the more exotic ones like the multi-layer graphene systems and so on. So I think much of what I'll tell you is relevant for this larger class of systems, even where there's not the exact same RS parameter to think about. Okay, good. So the things I'll tell you about today are mostly summarized in this archive preprint with Dmitry Zverevich, who's a graduate student at the University of Wisconsin, and my colleague, Alex Yevchenko. And if this subject of electron crystallization is interesting to you, then I encourage you to go look at a recent review article we wrote that should hopefully be appearing soon in print with Tomasz Smolensky who's my experimental collaborator at the University of Basel, and Yo Zhou at the University of Maryland. Good. So let's jump in. So let me first of all tell you what I mean by a paired electron crystal. So the original idea that is going to motivate our discussion actually goes back to an observation made by Ashcroft and his student in the early 90s, where they made this the following interesting observation. They discovered or proposed, let's say, a new low density phase of interacting electrons, the paired electron crystal. So if you look at their abstract, what they observed is that for a range of densities or a range of RS values, the compensated low density interacting electron system possesses a ground state crystalline phase with zero angular momentum spin singlet pairs. So you can literally imagine a crystal composed of pairs of electrons which have total angular momentum 0 and form a spin singlet. Okay, so this was quite an interesting observation. It was suggestive of some kind of local pairing mechanism that was driven purely by Coulomb interactions. This was subsequently developed further, both in papers by Ashcroft and also by some of his scientific offspring. And the ultimate conclusion was that, at least in 2 dimensions, the transition from an ordinary Wigner crystal with just 1 electron in each unit cell to a paired crystal happens when this RS parameter roughly lies in this range between 20 and 30, where the system is most likely already a liquid. Okay, so the conclusion was that probably this kind of paired crystal was never actually the ground state, but it was a close competitor in terms of energies. And this, I think, was a sufficiently interesting proposal that I'd like to explain to you, at least briefly, what the kind of underlying mechanism is for making such pairs of electrons. Okay, so let's get into that. So actually, before discussing the paired electron crystal, let me tell you how I would like us to think about the ordinary, or I'll call it monatomic Wigner crystal. Okay, so deep in the Wigner crystal phase, where the system is essentially classical, we can imagine point-like electrons that are crystallized in this triangular lattice with a lattice spacing A0, just determined by the electron density in the system. And of course, this picture does not account for the fact that the electrons are actually quantum mechanical. They're not really sitting still at these lattice sites. They're executing zero-point motion in the harmonic confining potential that's generated by all their surrounding neighbors. So really a more accurate representation is one like this. So here I'm focusing in on this electron. So it's sitting in a harmonic confining potential that's determined by its interaction with all of the other electrons in the system. And that interaction is packaged into some effective stiffness of this potential. And the electrons have some width, C0, living in this harmonic potential. And this kind of picture then suggests a way of estimating the ground state energy of the crystalline state. We can do it like this. So the ground state energy per particle, we can write as the classical Madelung energy. This is just the classic electrostatic energy of building a triangular lattice electron solid. Okay, just add up all the Coulomb energy. Okay, plus a quantum mechanical term, which is the zero-point motion of each electron in the well generated by its interaction with all its neighbors. So in this kind of decomposition, the energy looks like this. This is the classical term, E squared over A0 times a coefficient of order unity that can be computed, plus the zero-point energy 1/2 h bar omega naught. Okay, so this gives us a way of estimating the energy of this crystalline state. Here I'm arguing for you on kind of qualitative or intuitive grounds that one can write the energy this way. This can be made more precise by using an appropriate variational Hartree type wave function. But this is the kind of picture that I want you to have in mind, that the electrons live in these harmonic confining potentials generated by the interaction with all their neighbors. And so this suggests then a way of thinking about a paired crystal, which is really the subject of our discussion today. So here, the way I'm drawing this paired crystal is literally just a 2-electron molecule occupying each unit cell of this triangular lattice. Here I'm drawing each of these 2-electron pairs as a ring. You'll see why I'm doing that in a second. Okay, and now there's some modified lattice spacing having to do with the fact that the density of pairs is half the density of the original electrons. Okay, and so we can then write down the ground state energy of the paired crystalline state in the following way. The ground state energy of PWC, paired Wigner crystal, is that of an ordinary Wigner crystal, where I view each of these pairs as a composite object of charge 2e, mass 2m with half the density. Okay, plus another more interesting term, which is the internal energy, epsilon naught, the internal energy of each of the pairs. And the factors of 1/2 here just come because the number of pairs is 1/2 the number of electrons, that's all. Okay, so there's this term, which we've basically already calculated in the previous slide, plus a new term that's a bit more interesting, and that's what we're going to talk about now. So how should we think about the internal energy of one of these pairs? Well, let's do and let me just say that this kind of hand waving, let's say, our decomposition of the energy can also be obtained from an appropriate variational pairing wave function of a sort of BCS type. Good. So how do we think about the internal energy of the pair? Well, we can again just zoom in on one of these pairs, okay, and open it up. Okay, so we see we have two electrons interacting by a Coulomb repulsion, E²/r, and they both sit in the harmonic confining potential, again, generated by their interaction with all the other pairs in the system. So we can think about this as a kind of effective two-electron quantum dot, if you wish, okay? And the effective Hamiltonian in this quantum dot looks like this. I have p²/2m kinetic energy for each of these electrons. They interact with a Coulomb repulsion term, and then they sit in this harmonic confining potential, okay? And as is usual in two-electron problems, we can make a translation to center of mass and relative coordinates, in which case the Hamiltonian looks like this. The Hamiltonian for the center of mass is just that of an ordinary harmonic oscillator. This is the part that corresponded to, this term, okay? And then the more interesting term, is the one here having to do with the relative motion, okay? So this is the term that's going to determine the internal energy of the pair. And so that's the one we're going to look at first. Good. So internal energy and structure of the pair. So this is the Hamiltonian for the relative motion from the last slide. Let me package these two terms together into one effective potential that I'm calling VQD, QD for quantum dot, because we're thinking about this as some kind of effective two-electron quantum dot. And you see that at small separation, the Coulomb interaction dominates. We have a strong repulsive barrier. And at large separation, the harmonic confining potential brings the electrons together. And so there's a well-defined minimum at some equilibrium separation R0, where the Coulomb repulsion is exactly balanced by the harmonic restoring force. Okay, so good. And in fact, in the large RS limit, where the system is semi-classical, we talked about that, we can even make an approximation to the energy levels of this Hamiltonian by just recognizing that if the system is semi-classical, then the 0-point motion of this two-electron molecule is small in comparison to the distance between the electrons. And so we can simply expand near the bottom of this potential and get some effective harmonic oscillator type levels. And so then the energy spectrum of this Hamiltonian, at least at large RS, takes the following form. It's determined by two quantum numbers. First of all, there's a constant term having to do with the energy at the bottom of this well, plus these harmonic oscillator levels with spacing h bar omega qd having to do with the curvature at the bottom of the potential. And the last term here, h bar squared m squared over 2 mu r0 squared, is just the angular momentum or the rotational kinetic energy of this pair, m being the relative angular momentum of the pair. Okay, so this is nothing exotic. This is just like the energy levels of an ordinary diatomic molecule from elementary quantum mechanics. It's like the roto-vibrational spectrum. Okay, there's the vibrational part, and then there's the rotational part. And so from this decomposition, we can immediately write down what the ground state energy of this pair will be. First of all, it'll correspond to the 0th harmonic oscillator level, and it'll correspond to 0 relative angular momentum, okay, because that costs rotational kinetic energy. So this is the ground state energy, okay? And the wave function will just be that of an ordinary harmonic oscillator, but now with this kind of funny structure, because the radius at the minimum is non-zero. So we really have a harmonic oscillator wave function that's peaked along a ring of radius r0 in real space with a width c, which is again just determined by the curvature at the bottom of this potential. So again, just to emphasize, the lowest energy state of the pair corresponds to 0 relative orbital angular momentum. And by the Pauli principle, because these are two fermions after all, the corresponding spin part of the wave function has to be a spin singlet. Okay, so these are 0 angular momentum spin singlet pairs that live at each of these lattice sites. Good. So now that we have a way of estimating the energy for both the ordinary and paired crystals, we can just plot those energies as a function of the interaction parameter Rs and ask, is there ever a crossing point? So the black curve is the ordinary or monatomic Wigner crystal, where we just have one electron in each unit cell. The red is the paired crystal, where we have, well, pairs of electrons in each unit cell. And here I'm reminding you that these pairs have 0 orbital angular momentum. And what we find, at least at the level of the approximations that we've discussed, is that there is indeed a crossing. So at large RS, the ordinary Wigner crystal dominates, and at sufficiently small RS, in this case, at RS of roughly 33, there is indeed a crossing point where the paired crystal becomes the state of lowest energy, okay? And again, the mechanism here is, the mechanism that drives this transition is actually a lowering of the 0 point energy of the paired crystal relative to the ordinary crystal. So it's a purely quantum mechanical effect. I mean, clearly, putting 2 electrons right next to each other is, in terms of Coulomb energy, stupid. It costs you a significant amount of Coulomb energy, but apparently in the electron gas, if RS is small enough, then that Coulomb energy can be compensated by a lowering of the 0 point vibrational energy. So it's purely a quantum mechanical effect in that sense. Okay, good. So yes, please.
So if you kind of put more pairs together, do you kind of expect it same trend to follow, or?
Probably, yeah. I haven't tried that calculation because treating. So here we had to solve a 2-body problem. Solving 3 and more particle problems becomes harder, but I think so. I think there should be some kind of maybe clustering effect in the test. Yeah. Good. And let me also say that the approximations we made in doing this kind of quantum dot picture and so on, they were kind of primitive. Really we have to remember that if I'm considering the 0 point motion of one electron, well, if this one is wiggling around, then that's going to get all the other electrons wiggling around. So the vibrations of this electron crystal are really collective. That is, one has to compute the actual phonon spectrum of the crystal to get a better estimate of the 0 point energy. And if you do that, and it was done by Tott in the early 2000s, you find that this transition actually moves to a somewhat smaller value of RS, roughly 20. But for our purposes, it's a bit, this kind of approximation is sufficient. Very good. So if you wish, we made a sort of Einstein model of the solid as opposed to a Debye model where we take into account the full phonon spectrum. Good. So we can append then this new discovery that we've made to the 0 temperature phase diagram that we discussed at the beginning of the talk. So as a function of electron density, what I'm telling you is that there can be apparently a transition from an ordinary monatomic Wigner crystal with 1 electron living in each unit cell to this kind of paired crystal. And that transition occurs when the dimensionless RS parameter is roughly 20, okay? But as we've also discussed, what we know with a good deal of confidence is that below RS of roughly 35, the actual ground state of the system is a homogeneous liquid, okay? And so it seems that at least in the ordinary 2-dimensional electron gas, there's no room for this kind of paired Wigner crystal state. But I think this is still quite interesting. The reason I think it's interesting is that this discussion we've had suggests that there is still some kind of local pairing tendency in the strongly interacting large RS regime. Remember, we discussed that when RS is big in comparison to 1, even in the liquid phase, the liquid knows about these very strong crystalline correlations of the proximate solid. Okay, and so presumably these pairing tendencies that we've discovered should also manifest in some way in the liquid state itself. So that's, I think, interesting. And let me also note that there was a very recent paper from the Flatiron Quantum Monte Carlo group that showed that actually adding a Moiré potential of the right periodicity can stabilize this kind of paired Wigner crystal. So there's some evidence that this state is really there. Good. So that's the status of this kind of paired crystal in the ordinary homogeneous 2-dimensional electron gas. For the remainder of the talk, I want to address the following question: is what does Berry curvature do to this paired crystal? Okay, if I imagine that the electrons live in a host band that has some significant amount of Berry curvature, how, if at all, does this story change? So this is not just an academic question. No, it's not just adding additional bells and whistles for no good reason. Really, this is motivated by, at least for me, it was motivated by some recent experiments that I found very exciting and interesting. from Longzhu at MIT, who in his group discovered in rhombohedral multilayer graphene some kind of exotic valley and spin or chiral superconductor. Okay, so actually here I'm showing you some phase diagrams from a more recent paper. So the original paper was 2025, where they discovered this chiral superconductor, and just last month they had another preprint appear in which they made the following observation. So I'll explain that to you now. First of all, let me explain to you what I'm even showing you here. So this is a two-dimensional phase diagram as a function of electron density and displacement field, or perpendicular electric field. And here you see at some intermediate densities and intermediate displacement field, this CSC, or chiral superconductor. Okay, this is a zero resistance state. And what they observed most recently in April was that if you heat this thing up, this is a 10 millikelvin, if you heat it up to a few hundred millikelvin, then the chiral superconductor melts, and it melts into some kind of resistive state that they've called R2 that seems to be some kind of actually electronic Wigner crystal. Okay, so this I think is very interesting because first of all, this is after all a low density electron gas, so presumably it's very strongly correlated for the reasons that we already discussed. This superconductor is proximate in the phase diagram to some kind of Wigner crystal phase, okay? And actually, I'm not showing it here, but if you take this same system and align it to the HBN substrate, then in this same region of the phase diagram, you get a quantum anomalous Hall effect, which is suggestive of an important role of Berry curvature. And finally, the superconducting coherence length, as inferred from measurements of HC2, suggests that the superconducting coherence length, or the pair size, is of the order of the inter-electron distance. So all of these observations, to me at least, suggest some kind of interesting interplay between this chiral superconductor and a Wigner crystal phase. And so the question then is, can we try to rationalize some of the character of this state, this chiral superconductor, by starting from the crystal? Yes, please.
So can you explain the red in the left part? Is this anything in this left picture, or?
So these are these highly resistive regions. Yeah, these are presumably smoothly connected to the undoped state, which is an insulator. But actually, I also have some questions about this region, so I'm not totally sure. But it's, yeah, most likely just some boring Anderson insulator type state. Yeah, but I'm not totally sure about that. But yeah, the states that I'm kind of most interested in are this one and actually this one. Yes, please.
Sorry, I maybe missed this. Like, how do you get the quantum anomalous Hall from the superconductivity?
So good. So if you take this kind of rhombohedral graphene, in this case it's pentalayer, five-layer graphene, and you align it with an HBN substrate, then the chiral superconductor goes away, and instead you get a quantum anomalous Hall effect.
I see.
Yeah. So that was.
What's
yeah.
the mechanism? Like, give effective. Okay.
I don't know. Yeah, unknown to me at least. Probably there are some theories, but I'm not sure there's any consensus. Yeah. Was that? Okay. Any other questions? Good. So the point of flashing these slides is to try to convince you that maybe there is some interesting interplay between electron crystallization and chiral superconductivity, and band Berry curvature, which is definitely significant in these graphene systems, might be playing some role in this interplay. So let's talk about that. So once more. Good. So let me just start by flashing our results, and then I'll explain where they come from. So this is a phase diagram showing different electron crystal phases in an electron gas with Berry curvature. Here I'm only focusing on crystalline phases, no homogeneous liquid phases or anything else. So here is our friend, the RS parameter that measures the strength of the interactions in the system. And on the vertical axis is Berry curvature in some units. And I'll explain to you in just a minute how we include Berry curvature in the model and what is the natural unit of measuring it. So when the Berry curvature is 0, then this is just what we've been discussing, that at large RS, we have an ordinary monatomic Wigner crystal. And as we increase the density or lower RS, this ordinary monatomic crystal gives way to this kind of paired crystalline phase. And now if we start to increase the Berry curvature, then there are a few interesting things that happen. First of all, the region of stability of the paired crystal extends to lower density. Okay, so apparently Berry curvature favors this paired crystalline phase. And probably what's most interesting is that if the Berry curvature is strong enough, then there's a transition where this paired crystal goes from having 0 orbital angular momentum pairs to pairs carrying a non-zero orbital angular momentum. Okay, so the system develops a chirality. In this case, the pairs carry orbital angular momentum -1. Okay, so these red arrows indicate that the electrons have now some angular momentum. So let me explain to you where this phase diagram comes from. Good. So the model we will consider is a valley polarized two-dimensional electron gas with Berry curvature. So the Hamiltonian is very similar to the one we already had. It's well, now it's written in a second quantized form. So we have p²/2m electrons, spinful electrons. They carry a spin degree of freedom, interacting by Coulomb forces. This is just the Fourier transform of the Coulomb interaction in 2D. But the way that the way that the Berry curvature is included is with these form factors. Okay, and when I say valley polarized, what I mean by that is that these form factors know about the Berry curvature, and the Berry curvature in the model only has one sign. Okay, so that means that time reversal symmetry is explicitly broken. So you can think about this Hamiltonian as describing, say, a valley polarized but spin degenerate electron gas. Okay, so in the model that we considered, which is one that was proposed a couple of years ago by Trithap Devakul and his student Tishwan Ten to study kind of related things, is one in which these form factors look like this. So in general, these form factors, they measure the overlap between block states of the host electron band. And in the model that we consider, these form factors have this Landau level type form, okay? E to the minus omega q², this exponentially decaying term, and this oscillatory term. And in this model, the Berry curvature is assumed to be constant and uniform throughout the Brillouin zone. So these should remind you of Landau level type form factors. So you can think about this as some kind of Hamiltonian for a dispersive, that's this part, Landau level type problem, okay? So there are two types of terms you see that enter here. The first one is a bit more innocuous. This exponentially damped term comes from the quantum metric of the host band. This is just to do with the size of the electronic wave functions that live in that band. And all it does when multiplied with the ordinary Coulomb interaction is suppress the interaction at large Q, or in real space, what that means is it just softens the Coulomb interaction at small separation because of the finite size of the electron wave functions. And the more interesting term is this oscillatory term. This is to do with the Berry phase that the electrons acquire as they move through the Brillouin zone in this band. Good. So with this kind of model, we now have two parameters to play with. We have the same RS parameter that measures the interaction strength, but now we have the Berry curvature and the natural units with which to measure the Berry curvature in this problem are, so first of all, you see that the Berry curvature has units of length squared. Okay, so to make it dimensionless, we should divide it by something with units of length squared. And here I'm dividing it by xi0 squared, where xi0 is the size of the localized electronic wave function inside the Wigner crystal. Okay, so that it turns out is the natural unit. So you can think about this alternatively as measuring the Berry flux in momentum space through the momentum space electronic wave function. Okay, that's one way of understanding what this dimensionless parameter is measuring. Good. So first, let's see what this Berry curvature does to the ordinary monatomic Wigner crystal, where we just have one electron in each unit cell. And in this case, it doesn't do anything very, very interesting. All it does is fatten this localized electronic orbital. So in the absence of Berry curvature, if we have some width xi0, then adding Berry curvature just enlarges the width by this factor. Okay, so if you're familiar with the semi-classical treatment of Berry curvature, then you can understand this as due to the fact that, well, Berry curvature in the semi-classical description enters as a sort of momentum space magnetic field that introduces a non-commutativity of the spatial coordinates. And so this fattening of the electronic wave function is just to do with the non-commutativity of the spatial coordinates. Okay, and the ground state energy per particle then in the crystal is modified in a very simple way. We still have the same classical electrostatic energy, but now the 0 point energy is modified to account for the fact that the size of the harmonic oscillator wave function is now bigger. Okay, that's it. More interesting is what it does to the paired crystal. So let's look at that. So here's our cartoon of the paired electron crystal. Here's our decomposition of the ground state energy per particle. Again, there's a term that has to do with treating each pair as a composite object of charge 2e and mass 2m. And then we have the internal energy, which will now depend on the Berry curvature in some way that we will now discuss. Okay, so again, the way we're going to investigate the internal energy of the pair is by opening up the pair. Remember, we had this picture of this as some kind of effective 2-electron quantum dot problem, where we have these 2 electrons interacting with Coulomb forces sitting in the harmonic confining potential from all the neighbors. And the way the Berry curvature enters into the description of the relative motion of the pair is in the following way. So first of all, the local Coulomb potential becomes a non-local integral operator. So it looks like this now in the Hamiltonian. And if anybody's interested, I can show you later what this non-local integral kernel looks like. And then it modifies the harmonic part of the Hamiltonian in this way, where curly A is the Berry connection that is related to the Berry curvature in this way. So here, the Berry curvature is really entering as a momentum space magnetic field, just like it would in the ordinary momentum for a physical magnetic field. Okay, so this is how Berry curvature modifies the dynamics of the pair. Okay, so we have diagonalized this full non-local Schrodinger equation, and I'll show you the results of that procedure in just a second. But before showing you that, let me first note that you can actually essentially understand what's going to happen by making an expansion for small values of the Berry curvature omega. So let me show you what you get if you do that. If I take that Hamiltonian from the last slide, this ugly non-local thing, and expand it for small omega, then I get a Hamiltonian that looks like this. It's the Hamiltonian we had for the relative motion in the absence of Berry curvature, plus this term in red, which, okay, I'm expanding in omega, so there's a term linear in omega, and there are 2 terms. There's one term that looks like this that depends on the orbital angular momentum m of the pair, and another term, grad squared VQD. Oh, let me remind you, VQD is this effective quantum dot potential. Okay, this term is to do with the quantum metric, the kind of size of the electronic wave function, and this term is to do with the actual Berry curvature and is more interesting. So having already diagonalized this problem, we can just treat this correction in first order perturbation theory. So I just sandwich this perturbation around the eigenstate, excuse me, around the eigenstates of this Hamiltonian, and you find a correction to the energy that looks like this. Okay, so this is the shift of the energy delta epsilon. There's a term that I'm calling epsilon g, which is positive and is independent of the orbital angular momentum of the pair, so I won't bother writing it, plus a more interesting term, which is linear in the orbital angular momentum of the pair. Okay, and it has some dimensionless coefficient alpha, and the units are just h bar squared over mu r naught squared, mu just being the reduced mass of the pair. Okay, and so the important observation is that this Berry curvature term tends to lower the energy of pairs with non-zero orbital angular momentum. Okay, in particular, it lowers the energy of pairs with negative orbital angular momentum. Negative means anti-aligned with the sense of the Berry curvature in the band. Okay, and let me remind you that by the Pauli principle, pairs with odd values of the orbital angular momentum will be spin triplet in order to maintain the anti-symmetry of the 2-electron wave function. Okay, so we then can already suspect that if the Berry curvature is big enough, it can bring down states with non-zero pair angular momentum. Okay, and so what we've done is just diagonalize this full monster here. Oops. You can do it numerically, and the results of that diagonalization procedure are shown here. So this is the internal energy of the pair plotted as a function of the Berry curvature, never mind the factor of 2, it's not important. And it's plotted here at a representative large value of Rs for a few different values of the orbital angular momentum of the pair. So when the Berry curvature is 0 along this axis, the state with 0 orbital angular momentum is the lowest in energy, and the m equals plus minus 1 states are degenerate. And now as we turn on the Berry curvature, you see that the green curve, the one with orbital angular momentum -1, comes down in energy, and there is in fact a crossing at some finite value of the Berry curvature where the the paired state with non-zero orbital angular momentum actually has the lowest energy. Okay, and these dashed lines are just the results of this perturbation theory calculation that we just discussed. So the conclusion then is that if you have enough Berry curvature in the band, the lowest energy paired state carries a non-zero orbital angular momentum. Okay, and if you increase the Berry curvature yet further, it turns out that there's a reentrant transition And it is again the zero orbital angular momentum paired state that is the lowest in energy. So if you're familiar with 2 electron quantum dots in magnetic fields, this is kind of like that, but different in that eventually you do go back to the zero orbital angular momentum paired state. But it's only for those of you familiar with 2 electron quantum dots in magnetic fields. Good. So let me maybe, how am I doing on time actually? I don't see. I think I'm okay. So maybe just mention very briefly that the structure of the pair wave functions is actually also sort of interesting. So here I'm showing you the radial wave functions of the pair plotted for different angular momentum sectors, and in each angular momentum sector, different values of the Berry curvature. So when the Berry curvature is 0, that's, I don't know if you can really make it up, but the green curves here, you see that the pair wave function is nodeless, as it has to be. But there's something interesting that happens, which is that as you increase the Berry curvature, this in each angular momentum sector, the lowest energy pair wave function develops nodes, actually for m equals 0 and m equals +1. So this seems to violate the nodal theorem that we know from elementary quantum mechanics. The reason that we are developing these nodes is actually to do with the fact that the effective Schrodinger equation that we were discussing is non-local. And it turns out that for a non-local Schrodinger equation, the wave function can develop nodes, the lowest energy state. The reason is that because you're convolving the potential with the wave function itself, by building in some oscillations, the system can actually lower its potential energy. But what's curious is that the m equals -1 state, the one that becomes favored for enough Berry curvature, actually avoids developing these nodes. So somehow it seems that one reason, at least, that this state is favored is that it can somehow take advantage of the oscillations that are already present in this kind of Coulomb kernel without having to pay the kinetic energy cost of developing additional nodes. Okay, so this is just a side remark. Good. So we can then summarize the situation with this phase diagram that I already showed you, which shows, again, that if you have enough Berry curvature in your band, then this paired crystal can give way to one in which the pairs carry some non-zero orbital angular momentum. Okay, so it's some cooperative phenomenon where you need both sufficiently strong Coulomb interactions for the electrons to want to crystallize and enough Berry curvature such that those pairs want to have a non-zero orbital angular momentum. Good. So let me then try to summarize. Oops, come on. Good. What have we learned? So I started by telling you that these electronic Wigner crystals appear to be ubiquitous across 2D materials in graphene systems and TMD systems, single layer, monolayer, few layer, twisted, untwisted. They seem to be all over the place. I have told you that in the experimentally relevant range of RS, or the experimentally relevant densities, these are quantum crystals in the sense that the 0-point motion of the electrons away from their lattice sites is significant. And I've argued for you that there is a strong tendency in the large RS regime towards this kind of local pairing of electrons. The last thing that we discussed is that if the host electronic band has enough Berry curvature, then that can stabilize a paired, first of all, Berry curvature stabilizes the paired crystal to lower densities, even with 0 orbital angular momentum, and enough Berry curvature can drive a transition to a chiral paired state where the pairs carry orbital angular momentum -1 and are in a spin triplet state. Okay, so it's some kind of local pairing mechanism for spin triplet. For spin triplet pairing. Good. So there are a number of questions that I think naturally arise. First of all, there's this question about making larger clusters of electrons that Marvin asked. Another question is there some analog? So these pairs are some kind of P plus IP type state. And so is there some analog of a topological P wave crystal that one could try to imagine? Other natural questions are what happens if you melt this kind of chiral paired crystal? Okay, what are the instabilities of that state? And finally, can this offer some kind of rationalization or local pairing mechanism for chiral superconductivity purely from repulsive electron-electron interactions? Okay, so then let me conclude by combining 2 seemingly unrelated parts of my talk. So I'm visiting you guys from the University of Wisconsin. Wisconsin, for those of you not in the US, you might not know, we are the dairy land of the United States. Okay, we make a lot of cheese, a lot of milk, and other dairy products. And another thing that came up a lot in my talk was Eugene Wigner. And it turns out that Eugene Wigner spent a few years in the 1930s on the faculty at the University of Wisconsin, I think 36 to 38. And before he left, Eugene Wigner was thrown a big going away party by the administration. And being the very gracious and polite man he was, he wrote a thank you letter to the administration, which is now displayed in the office of one of my colleagues. And in that thank you letter, he included various doodles of himself, self-portraits. So this is a self-portrait of the great Eugene Wigner eating, or biting into, I should say, a large wheel of Wisconsin cheese. And in the letter, he comments that the cheese was big enough, and in fact, it was somewhat bigger than he had expected. So let me conclude then by thanking you for your attention. I hope the cheese was big enough, and I hope we have some time for questions if there are any. Yes, please.
Yeah, thanks. Great talk. So if I understand you correctly, the Berry phase can, make it possible for you to enter this state.
Yeah.
Does the Berry does the Berry phase affect the liquid range at all?
I have no idea.
Otherwise, it could just eat.
Yeah. So good. I intentionally did not include any liquid phases here because I don't know how to do these calculations in the liquid phase, even in any approximate way. My hope is that, because the Berry curvature is stabilizing this paired crystal over a broader range of densities, it might survive.
Yep.
But unfortunately, at least at the moment, I don't know how to even estimate, the region, the melting of this kind of thing. I wish I knew how. And if you have any ideas, I'd love to hear. Yes.
So between the first, I guess, Wigner crystal and paired Wigner crystal,
Yeah.
Are there like these imaging measurements? Can they tell the difference, or I imagine it kind of looks the same to the.
Yeah. So if it was there, I think they probably would be able to resolve some difference. I think in the systems that have been imaged, I don't really expect this state to be there. It's mostly been in the TMD systems, which don't have very much Berry curvature near the bottom of the band. But my hope is that in some of the graphene systems, particularly this rhombohedral graphene, they really might be those might live somewhere here.
How would you see like the angular momentum in the?
So I think probably maybe a simple way would be to look at, if you could, the spin. So these are spin singlet pairs, and these by the Pauli principle are spin triplet. So that would be one the magnetic response would be very different between the two. Yes, please.
So if I don't do the calculation, like how do I know, like intuitively, how do I know like m equal to -1 should be the lowest energy or should be more stable than the other ones?
Yeah, so I can tell you what my original intuition was, but that intuition was wrong. Originally I had thought about the connection to 2 electron quantum dots in real physical magnetic fields. In that case, you get similar transitions where, at zero magnetic field, you have. So if I just focus on one of these pairs, imagine just a real 2 electron quantum dot, then the pair looks something like this. And if you put that in an orbital magnetic field, then the orbital Zeeman effect will bring down states of larger and larger orbital angular momentum, and that leads to these so-called singlet triplet oscillations. Mm-hmm. And since the usual kind of folklore is that Berry curvature is like a momentum space magnetic field, I thought that something similar might happen. And it does, but I think the mechanism ends up being quite different. It's not any kind of orbital pseudo-Zeeman type effect. It really is somehow connected to the 0-point motion. But unfortunately, I have no, as of yet, at least very simple way I can see it. I think the simplest way is with this kind of perturbative Hamiltonian that I showed you here. And this kind of Hamiltonian, actually, I should have said it before, is quite generic for systems with Berry curvature. That is, if I take any kind of 2 electron problem in a band with Berry curvature and look at its behavior for small small values of the Berry curvature, it'll look something like this. So for example, if I take a gapped graphene system and project onto the conduction band, then I will get a Hamiltonian that looks just like this, with omega going like 1 over the gap size. And this will actually be the same also in bands where the Berry curvature is non-uniform. So at least this kind of Hamiltonian is sort of generic, and this type of term I think will generically favor this kind of non-zero orbital angular momentum pairing, but I don't have a very simple intuitive understanding. Yes, please.
So in terms of broken symmetries, this paired Wigner crystal state, can I distinguish it from a normal Wigner crystal? I mean,
Yeah, so it'll have a different, first of all, yeah, a few differences. So it'll have a different periodicity, right? It'll have a larger lattice spacing. So if you can infer that, that's one way. If
I see things in a structure factor that has to do with like the form factor for the.
So the magnetic response will also be very different. So even putting aside this question of chiral, or non-zero orbit and orbital angular momentum pairing, in an ordinary where do I have the picture? Maybe here. Here in this kind of Wigner crystal, the electrons still carry their spin degrees of freedom, but they turn out to be very weakly coupled in this range of RS. So basically, you just have free spins. And so if you were to measure something like magnetic susceptibility, you would see down to probably tens of millikelvin, just a beautiful Curie law all the way through. Whereas here, the electrons form a spin singlet. So you'd have a totally different, significantly suppressed spin response. So those are a few different ways I think that you could try to.
If you could do so, I think they used to do electron scattering off of Wigner crystals. With a Wigner crystal on the surface of helium.
Oh, right.
And do electron scattering. So do you see things like the structure factor? Coming from?
Well, I guess the structure factor would know about the periodicity, right?
Well, I mean like knowing about the structure of the unit cell. So factors
indeed. Yeah. Oh, right. Correct. Yes, indeed. So there would be, the fact that you have, a more intra-unit cell structure would definitely show up, something like that. I don't know how that kind of thing could be done in, the kind of 2D materials that we're playing with now, but yeah, that's a good point. Yeah, very good. Other questions? Yes, please.
You assume that you could work with an average Berry curvature,
Yes,
but in practice, it's probably very inhomogeneous.
that's right.
And what does that do to your energy calculation?
Yeah, so quantitatively, I have no idea. So just to be honest, sorry, let me go back to the Hamiltonian. So the Hamiltonian I wrote down is not a realistic Hamiltonian for any 2D material. So this one, it's a toy model where I can just add in some minimal way Berry curvature to an ordinary 2-dimensional electron gas. If I want, and one with uniform Berry curvature, which as you say is not very realistic. So the kind of system that I would like to apply this to is like this rhombohedral graphene. So in that case, first of all, the dispersion is totally different. It's much flatter near the bottom of the band. And the Berry curvature is highly non-uniform. So that would presumably quantitatively change a lot of this. I haven't done those calculations. I think I kind of know how to do them, but I haven't done them. But I do think that the general mechanism might still survive, just because this kind of Hamiltonian is that this one is actually quite generic. So here, this omega could have been K dependent, and it would still go through actually. The structure of the Hamiltonian would look like this. I mean, the details would be different, but this kind of term would still exist. And this kind of term does tend to lower the energy of pairs with non-zero orbital angular momentum. But I want to do that calculation and I haven't done it, which is the honest answer. But I think, trying to generalize this to more realistic models, both in terms of the dispersion and in terms of the distribution of Berry curvature is something that
you would expect it to do something interesting because very few of the electrons would be submitted to a really large value of curvature, and all the others probably have flat space.
That's right. Yes. So yeah, stay tuned. We'll do those calculations. Anything else?
Let's thank Ilya again.
Yeah.